Now, let's consider the electronic structures of solids. Here, we use lithium as an example. The electron configuration of lithium atom is shown below. 2 electrons occupy the 1s orbital. So, the K shell is closed. The valence shell is the L shell. 1 valence electron occupies the 2s orbital. When 2 lithium atoms form a dilithium molecule, the bonding and antibonding 1s orbitals are filled with 2 electrons. The bonding 2s orbital is filled with 2 electrons as well, but the antibonding 2s orbitals is empty. Imagine, when 1 more lithium atom is added to the system, there will be 3 1s molecular orbitals, each of which is filled with 2 electrons. There will be also 3 2s molecular orbitals, which are half filled with electrons. When n lithium atoms bond together, there will be n 1s molecular orbital, each of which is filled with 2 electrons, and n 2s molecular orbitals which are half filled. If the number of atoms approaches infinity, the energy differences between the states from a single atomic orbital approach infinitesimal. The band theory is a theory to describe the electronic states of solids. It says that the electronic states in solids have continuous energies in different ranges. The energy ranges with states are energy bands. The energy ranges without states are band gaps. The Fermi level is the highest energy that electrons can possibly have in the ground state of a solid. For example, in solid lithium, the states from the 1s orbitals form an energy band. The states from the 2s orbitals from another energy band, etc. There is a band gap between the 2 energy bands. The Fermi level is in the band from the 2s orbital. The conductivities of solids depend on their band structures. If a band is empty, it does not conduct electricity because there is no electron to carry the charge. It is like an empty street with no flow of people. If a band is filled with electrons, it does not conduct electricity either. It is because every electron is locked down in its own state and cannot move freely. It is like the crowd which can hardly move. If a band is partially filled with electrons, it conducts electricity. It is because the electrons near the Fermi level can change their states in electric field. It is like the street with a few people. Therefore, conductors must have their Fermi levels in one of the energy bands. With band theory, we can categorize solids into metals, semiconductors and insulators. Metals are typical conductors. Their Fermi levels are in their energy bands. In contrast, semiconductors and insulators have their Fermi levels in their band gaps. The difference between semiconductors and insulators is that semiconductors have smaller band gap than insulators. There is no clear boundary between semiconductors and insulators. Generally speaking, if the band gaps with Fermi levels are over 4 eV, the solids are considered to be insulators. If the band gaps with Fermi levels are below 4 eV, the solids are considered to be semiconductors. For example, diamond is a typical insulator, while silicon is a typical semiconductor. The solids have diverse resistivities. Conductors have very low resistivities. Insulators have extremely high resistivities. Semiconductors have medium resistivities. The conductivities of solids depend on their densities of charge carriers which are free to move. In semiconductors, the bands below and above the Fermi level are called the valence band and conduction band, respectively. If all the electrons occupy the lowest possible energy states, as described by the Aufbau principle, the valence band is filled and the conduction band is empty. Thus, the solid cannot conduct electricity. However, above absolute zero, electrons have thermal energy. A small fraction of electrons in the valence band are excited to the conduction band. The empty states left in the valence band are called holes. The holes are equivalent to positively charged particles, which are free to move in external electric field. The electrons in the conduction band and the holes in the valence band are called charge carriers. They conduct electricity. Pay attention that, in electronics, the term electron refers to the electron in the conduction band, not all the electrons in the solid. According to the compositions, semiconductors can be categorized into intrinsic and extrinsic types. An intrinsic semiconductor is a pure compound without dopants. A dopant is a trace of impurity element that is added to a substance to alter its properties. In intrinsic semiconductors, the numbers of electrons and holes are equal. The Fermi level is at the center of the band gap. For example, pure silicon is a typical intrinsic semiconductor. An extrinsic semiconductor is a semiconductor with dopants. The dopant atoms substitute some atoms of the base semiconductor. The numbers of electrons and holes are usually different in extrinsic semiconductors. The more abundant charge carriers are called majority carriers, which are primarily responsible for current transport in a piece of semiconductor. The less abundant charge carriers are called minority carriers. If a dopant atom has more valence electrons than the base semiconductor atom, it is an electron donor. A semiconductor with electron donor has more electrons than holes. Thus, the majority carrier in such semiconductor is the electrons. Such semiconductors are called N-type semiconductors. N stands for negative because the majority carrier is negatively charged. The Fermi level in an N-type semiconductor is closer to the conduction band. For example, silicon has 4 valence electrons. Phosphorus has 5 valence electrons. Thus, phosphorus-doped silicon is an N-type semiconductor. The extra electrons are free to move in external electric field. That is why an N-type semiconductor has higher conductivity than the intrinsic semiconductor. If a dopant atom has less valence electrons than the base semiconductor atom, it is an electron acceptor. A semiconductor with electron acceptor has less electrons than holes. Thus, the majority carrier in such semiconductor is the holes. Such semiconductors are called p-type semiconductors. P stands for positive because the majority carrier is positively charged. The Fermi level in a p-type semiconductor is closer to the valence band. For example, silicon has 4 valence electrons. Boron has 3 valence electrons. Thus, boron-doped silicon is a p-type semiconductor. The electrons can move in external electric field to fill the holes. That is why a p-type semiconductor have higher conductivity than the intrinsic semiconductor. When a p-type semiconductor and an n-type semiconductor with the same base intrinsic semiconductor connect to each other, a p-n junction is formed. Due to the difference in their Fermi levels, the electrons in the n-type semiconductor diffuse to the p-type semiconductor. At the same time, the holes in the p-type semiconductor diffuse to the n-type semiconductor. As a result, negative charge accumulates on the p-type side of the junction, while positive charge accumulates on the n-type side of the junction. A depletion region is formed at the boundary, with a built-in voltage due to the extra charges on the p-n junction. The built-in voltage compensates the difference in Fermi levels before contact. The Fermi level becomes uniform in the whole system. Thus, the charge carriers stop diffusing. The built-in voltage also alters the energies of conduction band and valence band. On the p-type semiconductor, due to the accumulation of negative charge, the band energies raise. On the n-type semiconductor, due to the accumulation of positive charge, the band energies drop. The device based on one p-n junction is a diode. The configuration when the n-type semiconductor is connected to a negative electrode and the p-type semiconductor is connected to a positive electrode is a forward bias. The built-in voltage is offset by the forward bias, so the electrons in the n-type semiconductor continue to diffuse to the depletion region. Meanwhile, the holes in the p-type semiconductor continue to diffuse to the depletion region as well. The electrons and holes in the depletion region recombine, like the relaxation of other excited quantum systems. Therefore, the diode conducts electricity with the forward bias. If the conditions are right, the recombination of electrons and holes emits light. It is the mechanism of light-emitting diode. If the n-type semiconductor is connected to a positive electrode, while the p-type semiconductor is connected to a negative electrode, the built-in voltage is enhanced, and there will be hardly any current. This configuration is a backward bias. In summary, a diode works as a rectifier, which allows current to flow only in one direction. When photons with energy greater than the band gap illuminates a p-n junction, they excite electrons from the valence band to the conduction band, leaving holes in the valence band. The electrons and holes are separated by the electric field in the depletion region. The electrons drift to the n-type semiconductor. The holes drift to the p-type semiconductor. Thus, a voltage is built between two semiconductors of the diode. It is the mechanism of semiconductor solar cells.